Hi everybody, welcome. My name's Marius. I'm a scientist with Brain Corporation. So we're talking about robots who learn. We got a little bit of kind of the mixture. It's perfect for Maker Faire. We got robots, we got computers, and artificial intelligence. Who is Brain Corporation? We're a research startup. We're focused on perception and learning. Most of us are about 5 right now. Most of us have Ph.D.s in neuroscience, computer science, robotics. We like 3 things. We like biology. We like how animals move about in the world and learn. We like computers. Most of our work is done on computers. And of course, we like robots. So we wanted to share with you some of the research that we're doing today and hopefully recruit you to help us train some of these robots. So having studied bioengineering, the question comes is like, why do animals have brains? And if you look here, you've got the top image. You got the larval state of a frog and a tunicate, which is a sea squirt. And when they're babies, they look very similar. So a frog, a tadpole, has a head, has a body, has a tail, it wiggles, it swims in the water. And the same with the tunicate. Now the tunicate, which is a cecidian, when it grows up, it settles on the seafloor and becomes a sea squirt. And all it does is it filters food. So the first thing it does after it attaches is it digests its own brain. Brains are there to move. So if it doesn't need to move anymore, if it doesn't need to learn anymore, the brain, which is mostly fat and salt, is really tasty. So it'd be a waste to keep it if you're not going to use it. So in biology, you need the brain, which is expensive. About a third of your energy goes to, a third of the delicious food you guys had here at the fair goes to feed your brain. A third of the calories go to feed the brain. So if you don't need it, you're going to eat your brain. And on the right side, the frog, well, the frog's brain continues to grow. Its eyes get big. It moves around. It looks for flies and eats and figures out where the good spots are to eat flies. So in biology, brains are there for movement and for learning. So what does the biological brain do? Well, roughly 2 things. So what you're doing right now is mainly your understanding the world, which is what we call perception. In controls, they call it estimation, but it's the same thing. It's making sense of the world. And that's why when you're at a show like this, lots of stuff going on. At the end of the day, you're pretty exhausted because you've seen so many things. Your brain's tired. You just want to sit down and not do anything. There's a lot of activity going on. So roughly the back half of your brain is there to help you understand the world. So you pick out the things that are important. You pay attention to things that are new. And that takes a lot of energy. Roughly the back half of your brain is dedicated to understanding the world. Now the other half is action. And that's once you've understood what the world is about, then you make a choice and you decide and you move muscles. So the front half of the brain is there for action. And learning is really when you combine the two. When I talk about personalities, when I talk about training, is associating a state of the world with an action to take. And it's no different in controls for robotics as it is in your brain. How about that? So the other important point I want to make about biological brains is that it's mainly about wiring. So the bigger the brain, the more wiring you have. So you heard the expression white matter, gray matter. White matter is wiring. Gray matter is the neurons in your brain. And your brain is about 80% wiring by volume or by mass. So again, the bigger the brain, the more wiring you have. The more neurons you have, the more you need to shuttle information back and forth. So the bulk of your brain is actually just wiring. And in fact, in silicon, so in computers, you've seen tons of computers, tons of boards, whatever, the bottleneck is not really computation, it's getting information back and forth, it's the wiring. And that is really the kind of the bigger part of the research. This is the biologically inspired, the neuromorphic type computing that everybody's after, which is to overcome this bottleneck in wiring. So, switching a little bit to computing. If you're going to build an artificial brain, which was kind of our stated goal, to take the best of biology, take the best of computers, and apply it to robotics, you're going to have to start with a brainstem. Now the brainstem is the structure you see here on the right, and it's kind of the middle part of your brain. It's the midbrain. It's the central hub. All of the information that you get from your senses and you control your muscles flows through the brainstem. The information from your from your eyes going back to your cortex goes through this. So it's like the hub. It's like the router, if you will, and that's where you start. So there's some basic reflexes and processing. There's some basic learning that goes on for very fundamental things like uprighting and balancing happens there. When you see movement or when you see a bright light, your eyes immediately move to it. That happens in your brainstem. That's a brainstem reflex. When you see on the TV shows where they have a person, they're not sure if they're dead or not, and they shine a light to see if the pupillary reflex, that's a little bit lower, but that's, and if you can move your eyeballs, that's a brainstem reflex. So what we wanted to do is put a lot of computation and a lot of information shuttling in a small platform that's safe. And I think the key is you can put a lot of processing power, you can have huge batteries, and then the robots don't become safe, they don't become accessible, and above all, they don't become fun. So we want to make something that's a little bit fun for everybody and safe so that you can put them in the house. And again, these are learning things, so they will make mistakes. And when they do, you don't want them to damage the wall or go through the wall. You want them to bump and then back off and not repeat that. So what we're going to show today, and I'm trying to flip the camera. There we go. This guy's alive, so I'm not gonna put him down. But there we go. So BSTEM is the board that we're using to do some of our research, particularly around moving robots, around movement and learning, like I mentioned. And BSTEM is our development board. We are in San Diego. And we work with Qualcomm, so we've got a Qualcomm Snapdragon. And again, because of the wiring, we wanted to start it with a chip that's really good at moving information back and forth in a low power fashion. So we have a Snapdragon S4 Pro. It's a dual core processor, 1.7 gigahertz. We put fully loaded 2 gigs of RAM, 16 gigs of flash. It's a full-bore computer, but above all, it's only 2 to 3 watts of power when you're running it full steam. So when we run the network on there, it's really low power, and I think it's the best in its class. So for battery life, so if you wanted to train and have some time on it, it's really cool. We've got a USB hub, audio in out, 5.1. This guy is being kept up by an accelerometer and a gyro, which we have on board, so we didn't skimp out on the sensors. And we put a magnetometer and a barometer. Got HDMI out. And we've got twin 720p cameras. And this is an important point. A lot of people just hook up webcams to your PC, which you end up using your processor cycles to decompress that stream from the camera. So you use a lot of cycles just processing the data from it. These are native, basically raw data coming in that we process in stereo. So we got 2 of them. And they're synchronized. So if you want to do any stereo work, this is ideal. We've got connector boards, so we can connect to Lego, we can connect to basically any DC motor with encoder input, RC cards, input and output. We can do just about anything. And battery inputs, 5-volt power. So this is our own little research board. And we'll talk more about that later. And of course, connectivity, and I apologize today, we're going to try to do a live training demo, but the internet here is basically shut down. There's 100,000 Wi-Fi networks here, so it's going to be very hard to do, but we got videos. So on board we have a full Linux computer. It's Ubuntu Linux. It's also got some real-time options so that it's more deterministic. All of the development, or most of the development, we do on board. So we do all of the programming on board. You can see we actually left these here. We got USB and the HDMI, so we program the network and then we take it out, and then we train it, and then we collect data, and then we go and plug it back in. So it's basically a desktop computer. I got Python, Java API, all of the IOs. We put ROS, OpenCV, FastCV. We don't want to limit ourselves to just biological stuff. We want to make sure that we have an OS and a full computer. For our scientific work, we use the NumPy and SciPy libraries and some great plotting utilities. In fact, this screenshot is what you would see when you power this up. So it's full HD resolution, great graphics processor on board. So what I talked about is the OS, and of course we have our brain, our neural network that runs these things. So now, about the 3D printed robot. So this is iRover, and I'll flip the camera here, you can see it. It comes in multiple colors. And do the light thing in front? Yeah. So right now, this is how they would be. This is a nascent network on there, but so they just have basic reflexes. But we'll get to those later. iRover was designed with a coordinated robotics lab at UCSD. Thank you, Nick. And it's a fully 3D printed robot, so anything that isn't basically wiring or switches or motors is 3D printed. It's about 30 or so parts. We did it in about 30 hours on a MakerBot 2. It's really cool because we can basically print anything and we can control anything. And with a 3D printed robot, you can print whatever you'd like, and then with our brains, you can train it to do whatever you'd like without any programming. So this is a mobile, this one is not on, but it's a mobile inverted pendulum, means that it balances on its own. So it's kind of like a Segway for those of you that are familiar with that. Center of mass is above the wheels, so if I don't have it on, as is the case here, if I don't have the wheel, oh, there it is, balanced it. There we go. Got a microphone and a speaker, which you probably can't hear. So you can actually talk to it and it'll reply to you. And we get about 3 to 4 hours of battery life with active use. And they're really fun to do. So I'll show you a video of the actual training, but right now what you see is some behavior. So this is a completely fresh brain. It doesn't do anything. It just has basic reflexes. It'll follow the ball. Thank you, Oleg. Our other platform, again in the spirit of build your own body, or build your own robot body, are these 2 Lego robots. So these are based off of the Lego Mindstorm set. And the same reflexes, the same 3D printed eyes. We have a little box with connector boards for the Lego system. And these will actually drive around, but unfortunately we can't connect to them because there's about 5,000 Wi-Fi networks here. What else was I going to say? All right, so yeah, they're 3D printed eyes. On the Lego, we have 3D printed boxes and 3D printed eyes, the same basic reflexes. And we've got battery chargers and monitors. So really, if you have a Mindstorms kit at home, you can take this, replace the brain, add the eyes, and you're good to go and start training it. All right. So the other thing I want to highlight is our training app. Do you have the, JB, do you have the? So we also like video games. So we like joysticks and we like to train it by moving it around. So the way you teach these things is like you would a little animal. So you show it, and that's why we have these glowing balls. Humans have a really great device for pointing. It's your finger. You can point to stuff. This is the finger for the rover. It's got a distinctive color that it could see. And then you drive it around. So when you show it, you gather you attract its attention, and then you drive it around and tell it what to do in different cases. So you can build different behaviors. And what we're going to show you in a video is a following behavior. So this is the app. It's on an iPhone right now, but it could be on an Android later. And then the app tells you, which is kind of cool because we know what the network is doing. We know it's learning. So it'll tell you whether you're consistent. It'll tell you how good of a teacher you are. So as you train it, you know, like a good teacher, consistent, repeats, is patient. These are the qualities that we can monitor and we can tell you back. You can also load behaviors, and you can try different personalities, different types of networks, things that learn quicker or slower. We have the old man or wise man and young fool. We have different types of network architectures that we do. And again, because we know what's in the brain, we can give you feedback, which an animal may or may not. You have to kind of read into it. And then from the app, you can manage the personalities, download memories, and have different, you know, kind of like in the movies. You know, you load memories and you unload memories. So that's kind of cool. So this is iRover. And right now it's a basic brain. Again, it doesn't do a whole lot outside of just a follow reflex. There we go. And then it'll also look for motion, so if you wave your hands, it might try to follow you, although it's really busy here. So the types of behaviors that we're aiming for you to teach is basically like what you would with a dog. So upright and look, learn to follow and find a ball and knock it over. Obstacle avoidance, that's a big deal. So it should learn to avoid things that come closer and go around them. So I'll show you a movie. So right now, this is in our office. It basically doesn't do anything, and now it's ready to learn. It's looking for the ball and it's looking for motion, so that's how you attract its gaze. And JB over there is showing it the ball. And what he's going to do is he's going to say, okay, when you see the ball go left, he's going to actually tell it to go left. And when you see the ball go to the right, he's going to tell it to go right. There you go. So this is the training process. There's no programming. You just have to go around your house and tell it to do what you want it to do. So once it's fully trained, you notice that he doesn't have the remote in his hand, the trainer. This is the trainer. For dogs use clickers. For different animals use clickers to attract their attention, and then you reward. This is the clicker and reward. This is its food, if you will. And then we trained it to go and find this thing and then stop and then knock it over. Because he doesn't like it anymore. All right. Videos. All right, so same with the Lego robot, same thing. Not a fully 3D printed product, but a somewhat 3D printed robot. So the eyes and the brain, which is where it matters. So here we wanted to go around some obstacles and find a target, and then we have this cutting blade that is in that robot. So we'll demo the video. All right. So we told it to go to do a slalom, if you will. So there's a plush toy, and then there's the blue trash can. And while it's training, it's not very accurate, but afterwards it gets a little bit better. And then he finds his it's a little bit faster. There we go. There we go. What's that? Logo. Oh, there's the two together. Is this another video, or it's okay? It's looping. Okay, cool. Okay. So thank you for coming. This is just a small glimpse into the research that we're doing. And again, we wanted to have a little bit of fun with it. So if you guys want more information on BSTEM or the robots or our developer programs, please sign up. Visit our site at braincorporation.com. We're going to be contacting people. We're going to try to get these things out in some form. And please follow us on Facebook and Twitter, or at BrainCore. Is that how you use it? Yeah, there's Twitter. So thanks for coming, and we'll be around here if you guys have any questions. Thank you.